So what's the key to solving most nuclear reactions? Conservation of nucleons. Conservation of nucleons. So 0 and what sum up to 24, and -1 and what sum up to 11. Now I get to look on the periodic table and write in magnesium. So I'll have some more challenging nuclear reactions in a second. So knowing a neutron has these numbers is helpful. A proton has these numbers. An electron, -1 and 0. Positron, +1 and 0. Photon, 0 and 0. So a beta particle is a high-speed electron. An alpha particle is a helium nucleus. So any questions on these species? They all play a role in nuclear reactions. So how do we know if something's going to be stable or not? Well, we have some rules or observations. We observe that all atoms with 84 more protons are radioactive. That's just a lot of electrons to stuff into a nucleus. So looking up there, we get to lead. That's 82. The next thing is bismuth. Next time you're feeling ill and you're chugging the Pepto-Bismol, read the label. It's got bismuth in it. Sure makes you feel better, but once you're a chemist. And so that's also interesting that lead is the end of a lot of radioactive decays for some of these more radioactive things like uranium, thorium, lanthanum, all these big heavy things that are radioactive. And on that periodic table over there, it says a lot of those radioactive things just have the outline. So there's that weird one, element 43, technetium, used a lot in nuclear medicine, a man-made thing. That's kind of an oddball thing. It is radioactive, right? Even though it's before. Now we can have radioactive hydrogen. We can have tritium. We have all these isotopes. Right, hydrogen's not radioactive, deuterium's not radioactive, but we saw last week we had some carbon-11. Carbon doesn't want to be carbon-11, it wants to be carbon-12 or carbon-13, and you might have heard of carbon-14 radio dating. All right, so we covered point A. Let's move on to B. Nuclei above the belt of stability undergo beta emission. Nuclei below the belt of stability undergo electron capture or positron emission, and this increases the number of neutrons and decreases the number of protons. So the most interesting thing on here, we have basically the atomic number of the element, because the atomic number of the element gives us the number of protons that atom has. And here we have number of neutrons. And so this line here is a 1-to-1 ratio, but as you pack in more protons into a nucleus, like charges repel each other, so it appears nature likes to stuff in neutrons to kind of give the protons space and make them stable. So this region here, we see that the neutron to proton ratio is increasing. We get up here to element number 53, iodine, and we see the neutron to proton ratio is 1.4. We take the number of neutrons and divide by protons and we get 1.4. Here you just get 1 everywhere. So obviously we have more neutrons than protons. Get up here to bismuth, 83. Now our neutron to proton ratio is 1.52. And so this swath here is of things that are stable, but we can have elements outside of this belt of stability and they're going to move in a certain direction. So what we see here with statement B, we see here with this slide here. It's like a blown up section. So when we have beta emission, we get a proton and we lose a neutron. And so that can do certain things for us. Loss of a positron or electron capture is going to take a proton and convert it into a neutron. And loss of a helium nuclei, atomic number 2, 2 protons, mass number 4, that means there's 2 neutrons. So this moves in this direction. So up here we can say above the belt of stability, it can, like here where my little pointer is, I can move this direction if we undergo beta decay, or loss of a high-speed electron. If I'm down here, we can move this direction with positron emission or electron capture. So here's a review, beta emission. Now normally we see elements like my examples on the whiteboard, but this is what's going on inside the nucleus. Here's a neutron turning into a proton and kicking out an electron. And so the elements we see here, like this thing here, that first example is what's going on inside. A neutron turns into a proton, kicks out an electron, and so that is the beta emission. Now here's something I find interesting. An electron encounters a positron, and remember I was basically joking when I said I like to think of the positron as antimatter. It's antimatter to an electron. So what happens when an electron and a proton find each other? They annihilate each other and turn into a photon. We get two photons. Good example of matter and energy maybe being interconverted. What might be interesting, can you slam two photons together and get an electron and a positron out of them? I bet you a nuclear chemist will tell you, or nuclear physicist, indeed you can under the right conditions. So notice this one here, positron or beta emission. Well, I got ahead of myself. The electron capture is really this thing written backwards. So here's a proton turning into a neutron and kicking out a positron, and here's a proton capturing an electron and turning into a neutron. So positron is a particle with the same mass as an electron but opposite charge. So if you look in the textbook, it will say magic numbers. So if I bought lottery tickets, which I don't, I'd be entering these numbers all the time, hoping they'd be magic. It says here nuclei with 2, 8, 20, 28, 50, or 82 protons, or 2, 8, 20, 28, 50, 82, or, big jump, 160 neutrons tend to be more stable than nuclides with different number of nucleons. So once again, this is just an observation from nature. Nuclei with an even number of protons and neutrons tend to be more stable than nuclides that have an odd number of these nucleons. So element 92, that would be uranium, uranium-238, and when you mine uranium, you get uranium-238 and uranium-235, and for quite a while, I told you when I was a kid I was confused about radioactivity, because sometimes it's a wave, gamma emission, sometimes it's a particle like the electron. So for years when they would talk about uranium enrichment, what is that? Yeah, 235. So I used to be under the impression that they wanted to enrich the 238 and use that to make nuclear weapons, but they want the 235. It possibly goes back to this thing here. It must be an odd, 235 is not an even number. It says here nuclei with even numbers of protons and neutrons tend to be more stable than nuclides that have an odd number. And 92, element 92, uranium, even number of protons, uranium-235 must have an odd number. All right, so this looks like plain old uranium-238. Notice neutrons decreased by 2, protons decreased by 2, and so this obviously must be an alpha emission, and we get thorium-234, and that thorium turns into Pa, and it turns back into uranium. Now we have uranium-234. No, it's not stable, and it turns into thorium, and it turns into radium, and it turns into radon, plutonium. So these are beta emissions: alpha decay, alpha decay, alpha decay, alpha decay, alpha decay, beta decay, beta decay, alpha decay, beta decay, beta decay, alpha decay, to lead 206. So large radioactive nuclei cannot stabilize by undergoing only one nuclear transformation. And so we see series for a lot of these things. So this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 decay processes before it gets to a stable nuclide. And lead 206 is lead's the end of the road for a lot of these because of that observation that anything over 82 protons is generally radioactive. Looks like I'm going to try and beat a dead horse here. There's those 14 things we just went over. We're going to forget about that and talk about this thing here, nuclear transmutations. Can we turn lead into gold? I'm going to look up there and find gold. I have ideas. Looks like if I back up, osmium, yttrium, platinum, they're probably more all expensive than gold anyway. I don't know if this would work out so great. But what is a nuclear transmutation? They're caused by collisions between nuclei. So for example, nuclear transmutations can occur using high velocity alpha particles. So here's some nitrogen. If we can shoot an alpha particle at it, we can get some oxygen-17 plus a proton. In the above reaction, nuclear chemists like to write this shorthand notation, and it basically says start out with nitrogen-14, shoot an alpha particle at it, comma, and you'll get a proton and oxygen-17. So when I was an undergrad student, I took a course called Modern Physics, and we created a bunch of radioactive material, and then we measured its half-life. And so what they had a lead barrel, and inside they had some radioactive material like uranium. And we had this thing called a rabbit, and it was kind of like the thing in the drive-thru at the bank where you put your paperwork and it goes down. So we had put in a little sample of like gold or some other metal, and it would go down and it would sit next to the uranium or some alpha emitter, I don't know what, and the alpha particle would get emitted and it would make the nitrogen radioactive. And this is really the problem with nuclear waste, is you have some samples sitting there and it can make everything around it radioactive. Like this form of oxygen might be radioactive. So the alpha particles being emitted from thorium or uranium can make other things in the vicinity radioactive. So to overcome electrostatic forces, charged particles need to be accelerated before they react. So here's a picture of a cyclotron, and it's a way to get a particle. So this is a vacuum chamber, and we have these two hollowed out metal shells and some alternating current, and we can impart some charged particle like a proton or an electron, and we accelerate it, and eventually we slam it into something, and that's how we can make it radioactive. So we've upped our game just a little bit. It says here, calcium-41 decays by electron capture. The product of this reaction undergoes alpha decay. What is the product of this second decay reaction? So what we're going to have to do is just probably look up at the periodic table and figure out the atomic number for calcium-20 electron capture. So now it's when we might need to look at that little table that had all our different particles, and we're going to figure out what that is. Then it says the product of this undergoes alpha decay, helium nucleus, or you can do the alpha symbol. It's got a charge because it has no electrons. So I sum these up, figure out this is 19. That's going to be potassium. And then I'm going to come over here and I'm going to have to look at this 41 and say 4 and what sum up to 41? I think 37 and 4 sum up to 41. Then I'm going to want to go 2 and what sum up to 19. That looks like fluorine. All right, you want to see the most challenging one I got? And so this will bring to light the last thing we just talked about, the nuclear transmutations. Bombardment. We're going to bombard something. There's my uranium. It's element 92. So bombardment of this with a neutron. So I might have to look at that table of all our particles and figure out this is what I want for neutron. TE, that's what I was thinking of. TE52 plus 3 neutron and a mystery element. Wow, all these zeros are kind of nice. I think I need to ask myself, what is 52 summed with what equals 92? 40. All right, now I can look up at the periodic table. Zirconium. That's how you tell your gal that you love her, right? Instead of a diamond, you buy her zirconium. All right, I'm being silly. All right, the next thing. Oh, look it. I have to take 135 plus 1 plus 1 plus 1 plus x equals what? There you, I think you got the thing that trips a lot of people up. It's over on this side, it's 236. All right, so let me see if I'm doing this right. I have to do it the most confusing way possible. All right, does this make sense? Did I do it right? All right, sorry I went over. We should finish up the chapter by Wednesday.